Cool. All right. How are y'all doing? We need to move the desk so we can take the test. Are y'all?
I had a nightmare about that.
You know we're here in that state of mind, right? Thinking fast is like, excuse me, I can close it off.
All right. Well, I was able to put the test together already. Yeah, so I'm going to hand it out now. So take something to write with because I'm going to verbally discuss the test. So you might want to just jot some things down. At this point, the exam's 14 questions long. I might trim it down a little bit. All right, so I mean, obviously I can't tell you exactly what is being asked, but the first question has 3 parts to it, and it's asking for exact values of some trig functions at some non-common angles. And so the angles that you're given are like, cosine of some angle, but that angle isn't exactly a common angle, but it's some combination of common angles. So this, remember, we're starting this test off in the section sum and difference formulas, right? Well, there's also trig equations, but that's going to come later. Sum and difference formulas. So find the exact value, no calculator on that. All right? Then the next one, I give you some information about sine of theta. I give you some information about cosine of beta. And then I ask for like sine of alpha or sine of theta plus beta, sine of 2 beta, sine of theta over 2. So you have to use all of your different formulas, but that given information, we did this, I don't know if you remember, we had to draw triangles, reference triangles. So it's critical you get those reference triangles right, because everything else, once you get them, do y'all remember me doing those? Right, the first few I got the triangles and then we filled it all out. And then after I'd done a couple, I said, look, I'm just going to get the triangles, and then the rest you could just plug into the formulas. Something to that effect. Well, actually, I don't know the exact. I think it was 8.6. I'm pretty sure that was 8.6. All right. Next, 2 parts to it. This is number 3. Find the exact value again. And all I can say about this is that both of these problems have like a trig function somehow combined with an inverse trig function. So like maybe you have a trig function and inside of it you've got an inverse trig function, and you got to kind of mess with it. And again, I mean, I'm basically laying the test out here for you without giving you the problem, so I think that's enough information for you to go through your homework and see what I'm talking about. But you will have to use formulas like sum, difference, double angle, something like that to do those problems. Okay, number 4, find the general solutions for a trigonometric equation. Number 5, find the general solutions of a trigonometric equation. Number 6, find the solutions just on the interval 0, 2 pi of a trigonometric equation. Pardon?
What did you say for number 6?
It's find the solutions on an interval 0, 2 pi of a trig equation. So the first 2 there that I mentioned, number 4 and number 5, were general solutions. I think those are easier, personally, because you don't have to create a list. And then number 6, you actually have to list them out, but it's actually not that bad. The problem with number 6 is trying to solve the equation. You got to figure out how you're going to solve this equation. All of these equations that I have in here either involve where the argument of the trig function is more than just theta. Maybe it's like 5 theta or 4 theta, which means you have to go through and divide. And again, I'm thinking you're going to go back and review. So I'm trying to give you hints. And then some of the other 2 equations, you have to use some sort of formulas to solve the equation. I believe one of them becomes quadratic. Let me see. Yeah, that one becomes quadratic. Okay. Number 7, find the remaining sides of a triangle. So I'll give you information about a triangle. You find the remaining sides. Number 8, find the remaining sides of a triangle. What do you think is something you should be thinking about if I'm asking you to do something using law of sines? What do you think is kind of a red flag danger zone area that you should be ready for? Where you have 2 triangles. With law of sines, there is that possibility you could have 2 triangles. I would expect that. I think I even said that when I presented it to you. And then let's see. Number 9, I'm asking you to look at a picture and make a comment of how good my drawing is. And that's it. No. It's a picture and there's some geometric stuff. You can kind of make out a triangle in it, and I ask you to solve it. I'm asking you to find the distance from a point to another point. So I am expecting you to use either law of sines or law of cosines there. And then number 10, we start with vectors. So find the magnitude and direction of a vector. I give you a vector, I show you a picture of it. I ask you to find its magnitude and direction. And then number 11, find a unit vector pointed in the same direction. Haven't talked about that. Number 12, find the length of a vector. Wait, no, sorry. I give you the length of a vector. I give you its direction, and I ask you to find its component form, which again, we haven't talked about. But I think when I cover this today, I'm hoping that you'll look at it and you'll be happy to see it on the test, because hopefully you'll find it as straightforward. We'll see. Let's see how you feel about this. This is why I said I might trim the test down. I might take some of this vector stuff off. But if I do that, just remember that's going to wind up on your final. So let's see how it goes. Number 13, I give you a diagram and I ask you a question, which, again, let's see how this goes today. That's pretty much it. Number 14 is just more vector stuff about adding vectors together, subtracting vectors. Yeah. Okay? That seemed like a good review? Other than me handing you the test? All right, let's talk about vectors. So last class we established that a vector is a geometric object that has 2 important characteristics. It has both a length, which we call the magnitude, and then it has a direction, which it points. Right? That's what we talked about. And that you can move vectors around and it didn't matter where they were as long as they pointed in the same direction, had the same length. So we're going to now look at what's called the algebraic form of a vector. The algebraic form of a vector. I also will refer to this as the component form. All right. So here's what we're going to do. I'm going to draw a really large XY axis here. And let's take our time to mark out some dashes here so we know where we are. So each of these dashes is 1 unit. Get the idea, right? Okay, so let me put a vector here. I need to have a line segment that has a direction. So we call that a directed line segment. I need to draw it, and it needs to have some length to it, or else it'll be the 0 vector, right? So let me see here. How about if I start out here, and let me go to, try and line this up here. So yes, that does go straight up from here. It's supposed to go straight over here like that. All right, so that is a vector, right? Let's call that vector V. V for vector. Okay, so that's how we represented a vector with that notation with the little, it's like an arrow on top that half of it's been cut off. All right, now I'm going to draw another vector up here. Make this one blue. So let's see. Started out here. End it here. That's just to help you reference like where these things are. What is this vector? What should we call it? What do you want to call it? Z? We can call it vector Z. You all agree? I love finding money in my pocket. It's like it when it's bigger than a $5 bill. Z, yes, we could call it Z. Just so you know, I mean, normally there's nothing wrong with Z. We like to use, books like to use V, W, U. Those are the most common letters you'll see for vectors. Z, you could use it, but normally we reserve Z as a variable. Like, you know how X is the normal variable we use? We use Z for a complex variable, a complex number. So X is a real number usually. Z we usually use in mathematics to represent a complex number. So I'm not going to use Z, not because I don't want to, but actually we can call this something else. Just pay attention to it. Do both of these vectors have the same length? They're the same vectors, aren't they? Doesn't matter if this one's here and this one's here. Doesn't matter. Do they have the same length and direction? So if we start from here, to get to this point, we went up 2 and over 1, 2, 3, 4, 5, right? Here, start here, we went up 1, 2, and over 5, yes? So these have the same pitch to them, same rise over run pretty much, and they are the same length, obviously, because if they have the exact same rise and run, then they have the same length. Make sense? So I could call that V also, yes? Well, I could say V1 and 2, but it is V, isn't it? I mean, this is V, that's also V, so that they're exactly the same vectors. That was the whole point from last class, is that doesn't matter where your vector is in the space, they are equivalent if they have the same direction and same length, right? So those are both V. So now what we're going to try and do is write this vector in what's called its component form or algebraic form. So what we do is we imagine that we're going to start at the, what do we call this? Oh, the origin's here. So if we started here, on the vector, this is called the tail of the vector, and that's the tip, remember from last class? Okay, so we start at the tail. Let's try and find our horizontal displacement, to get to here, horizontal. So how far do I have to move to go from here horizontally to get up to that point? 5 units, right? And then what is my vertical displacement? It's up 2, right? So those are important quantities because those also, that is exactly what's happening here also, right? And that by itself should be enough to define the vector. Somehow writing down the horizontal displacement and the vertical displacement. Make sense? And that's what the algebraic form of a vector is. It is something that represents its horizontal and vertical displacements. And we list them out in that order, horizontal and vertical. And let me show you how we write it. We will say v, the vector v, is equal to, now let me write the horizontal displacement was 5, and the vertical displacement was 2, right? 5 comma 2? Now, that's kind of, seems incomplete. That doesn't seem right. That seems, just to list two numbers with a comma is weird. So somehow I need to let you know that this is a vector and not a point, not to be confused with the point 5, 2, because where's 5, 2? 1, 2, 3, 4, 5, up, 1, 2. This is the point 5, 2, isn't it? That's not what I'm talking about though, right? I'm talking about the vector that has a displacement of 5 horizontally and a vertical displacement of 2. So what we do is we put what we call angled brackets around this. If we slap angled brackets around it, then what we're doing is we're telling everyone, hey, this is a vector. This is a vector, and this is its horizontal displacement, and this is its vertical displacement. Regardless of where you position it on the XY plane, okay? Make sense? Angled brackets. If you don't know what those are called, parenthesis, right? Bracket is this, and angled bracket is this, right? So we reserve that angle bracket notation for vectors. This right here is called the horizontal component. And this right here is called the, what do you think? No, it's up, down. Up, down. No. The vertical, yes. Vertical displacement. Vertical component. Sorry. I was actually thinking of something I wasn't. Okay. Component. I was thinking of this story when I was a kid. I was driving by this I don't know if you've ever seen this, like in a neighborhood. Have you ever seen that picture in a neighborhood? It's like a crime thing. You know what I'm saying? Like a crime. Yes?
Yes.
Okay, so like I was a little kid, I was driving with my dad, and I was like, Dad, why does that sign have a ship going over a hill? And he's like, what? And then he's like, no, it's a guy with his coat and a hat and hiding or something like that. I was like, oh, okay. So I always thought this was a ship going over a hill. It looks like a ship going over. I'd still draw it like a ship going over a hill, like a little sailboat, right? Y'all see it going over the hill? But what made me think of that is I always got horizontal and vertical confused when I was a kid too. So the horizon, right? That's obvious now. It's all obvious to you. Some things just slipped my mind as a child. All right, questions on the notation for this? While we're here and while we're trying to get this language clarified, what are these called? Like in a point. These are coordinates. These are coordinates. Okay? Coordinates. It's the x coordinate and y coordinate, right? Here, they're called components. And you can, and if you go on to calculus, we actually call this the x component and the y component. Not to be confused with the x coordinate and y coordinate of a point. All right, so that's the picture we have. That's the algebraic form of the vector, or if you'd like, you can call that the component form. Make sense? Okay. Now, in general, a vector can be written V equals angle bracket V1 comma V2. So this is the standard component form of a vector. This was a specific example where V1 was the 5, right? And the V2 was 2, yes? So V1 and V2 here are just numbers. Agreed? They're just numbers, but they give you the horizontal and vertical displacements respectively. All right. Let's move on. Let's talk about the length of a vector. Well, if we want to know how long a vector is, one thing we could do is this. Imagine drawing some arbitrary vector, and from that vector, constructing a right triangle out of it, like this. So this is the vector v, right? This is the vector v. I want to know how long that vector is, its length. Do I know how long, or the distance from here to here? If I have its component form, do I know the distance from here to here? It's v1, isn't it? Yes? This would be v1. And the horizontal displacement should be v2. Right? All right. Now, by the Pythagorean identity, right, we have a squared plus b squared is c squared. So this side should be the square root. So this side right here should be the square root of v1 squared plus v2 squared. Make sense? We call that the magnitude of the vector or the length of the vector. Now, we have a special notation for it, all right, that lets everyone know we're talking about the length of the vector. And here's the notation. This is what we do is we write the vector v, and we put those good old absolute value bars. Remember the absolute value bars? Those absolute value bars actually have a more general meaning than what you know. You always look at the absolute value of a number as being like whatever the number is but positive, right? Well, the absolute value actually measures length is what it does. So when you sit here and you go, hey, what's the absolute value of -4, right? Everyone says, oh, that's 4, right? What that actually means is if you look at a number line and you go to -4, measure the distance from -4 back to the origin. How long is that distance? That's 4, right? Well, this is saying measure the length of v, okay? And the length of v is this, okay? So this is the new notation that represents the length of a vector. Let's look at some other properties of vectors. We said that all vectors have to have a direction, don't they? We have to have a direction. Well, when we talk about directions of a vector, we could say like this angle right here, couldn't we? But that means we all have to agree that whenever we talk about vectors, that the x-axis out to the right is always going to be 0 degrees. We have to all agree on that, don't we? I mean, we have to all agree on what 0 will be, because that way we'll get the same answers for angles, won't we? And since we've already used the x-axis out that way as 0, like the whole time we've been in this class, let's just stay consistent and still call that 0. So if this is 0, this angle in here we can call theta. And that would be the direction of the vector. Okay? So theta in that picture is the direction of v. And can anybody see a nice, like imagine somebody gave you the components, right? Somebody gave you the components. Is there a way that you could then take the components and spit out the theta? Like give me what theta is. How? Yeah, okay. You're right. You could use the idea that tangent theta would be what? V2 over V1, right? And if you wanted to know what tangent was, you would just do arctangent on both sides, wouldn't you? Arctangent of tangent would give you just theta, and arctangent of the right side, well, that you would have to calculate on a calculator, right? But this is a way that you can get the angle. So there are two big formulas here. If somebody provides you a vector v, and they give it to you in component form, that means you have v1 and v2, this is a formula that spits out the length of the vector, right? And this is a formula that spits out the angle or direction of the vector. Is there anything I should be worried about over here with this arctangent? Anything I should be worried about? The domain restrictions. See, because I'm going to be using arctangent, I know that when it tries to spit theta out to me, right, it is only going to be looking in the first and fourth quadrants because the domain restrictions on arctangent are between negative pi over 2 and pi over 2. That could potentially be a problem, right? What if my vector is pointed this way like that? Then what's the angle? If this is 0, the angle is going to be bigger than pi over 2, right? Bigger than 90? So if I do this calculation, it's not going to spit that angle out to me. So I'm going to have to be very careful when I do the calculation of theta. We'll do an example, all right? Just I'm trying to look ahead. Any questions on this so far? You ready to do an example? All right, so let's do our first example here. Okay, this is the vector v. All right, there it is. First question is to find component form. Of v. Second question, find this. Third question, find direction of v. All right, so how am I going to find the component form? What do I need to find the component form? I need both the horizontal and vertical displacements, don't I? All right, well, let's look at this from a different perspective. Something we didn't need earlier, but let's do this now. Let's actually write down these two important points as ordered pairs, as normal points. This is the point -2, 2. This is the point 1, -3. Everyone agree? So how can I get the horizontal displacement? You could count it, but won't it always be the difference in the x-coordinates? In other words, if I'm trying to go from this point down to here, I need to go from here across first, right? So that distance should be this number minus this number. With me? So I'm going to go to find, I'm trying to find v, and I'm trying to find the components. v1 should be 1 take away -2. you're trying to find the distance between 2 points, you subtract to find the distance. So does that spit out the right answer? 1 take away -2 is 1 plus 2, which is 3, isn't it? So isn't this displacement 3? 1, 2, 3? All right, so that works. Would it have worked the other way around if I would have done -2 minus 1? It would have been backwards. It would have been negative, wouldn't it? And that's not right because we're trying to go from here to here. Tail and tip make a difference. So what I did is I subtracted the x coordinates, this one minus this one, and then I do the same with the y. I'm going to do -3 take away 2 to get the v2. -3 take away 2. So what is our v in component form? 3, -5. See, because your horizontal displacement vertical displacement was down, wasn't it? And when we go down, that's negative. So we went to the right 3 and then down 5. Yes? All right. Have we answered part A? Yes? Any questions on that? Okay, how about part B? Find the magnitude of V. How long is that vector? So we're going to do the magnitude of V. The formula is the square root of V1 squared. What's V1? 3, right? So we're going to go 3 squared plus now V2, which is -5 squared. So this is the square root of 9 plus 25, which is 30, no, wait, is that right? Oh yeah, root 34. That's the length of the vector, right? That's how long it is. And then finally, the direction. So to get C, we use the formula that theta is arctangent of, which one was it? Was it V1 over V2 or was it V2? It was V2 over V1. Right? It's like the y over the x. That's what tangent is defined as, y over x. So I'm going to do arctangent of V2, which is -5, over V1, which is 3. And I'm going to get on my calculator. And I'm going to do this in degree mode so that I get my answer in degrees. Good thing I checked. I was in radian mode. So I'm going to do arctangent of -5/3. I'm getting -59 degrees and some change, but approximately -59.04 degrees. Anyone else get that? Okay. Now, we have to double check to make sure that that makes sense. Does it match our picture? So remember, if this is our vector right here, we're going to look at pointing out horizontally, right, like this, as 0 degrees. -59 degrees would be a rotation this way. So it seems to match up, right? Any questions? All right, I'm going to change the problem. So I'm moving on to another example, but I'm going to do just one simple change. Ready for it? I'm going to change our vector the other direction. And we're going to see how this impacts the answer. So our vector now goes from here to here. And we'll call this a new example, so I'll still call that the vector v, okay? What is the difference that we have in part A, in the computation of v1 and v2? It's backwards, right? I need to flip it over. So look, when I do this computation, instead of doing this number minus this number, we're going to go this number minus this number. So that's one of the biggest mistakes students make when they're trying to figure out the components of a vector, is they get the 2 points and they forget which one do I subtract from which. So always just think, you start out at the tip, subtract from the tip, you subtract the tail. Okay, so subtract, take this number, subtract this one. If you're going that direction, that minus that. So I'm going to do -2, take away 1, and then the other one is 2, take away what? -3. So what's the difference in our vector here? What does it look like? What's the component compared to that one? Hello? Hello? Is this working? Is this on? Can you all hear me? -3, 5. Yes? -3, 5? So our horizontal displacement, to get from here to here, we go left 3, that's negative, and we go up 5, so that's positive, as opposed to positive 3 and down 5. See the difference? Okay. Now, does anything change here with our length? Well, this is minus, right? And this one's plus. But does that change our actual value here? It doesn't. And it shouldn't, because all we did was flipped it over. We didn't change how long the vector was, right? So this is still this. What about the angle? What changes here? Instead of -5 over +3, it's actually +5 over -3. Wait a minute, though. Doesn't a negative not matter if it's on the top or the bottom? Like if I have -5 over 3, it's the same as 5 over -3. So our calculator has no idea which of these was negative. That's why the calculator is going to spit out an answer that might be wrong, because it doesn't know if it was -5 over +3 or 5 over -3. Do y'all understand what I mean by that? So you would type this into the calculator and you would get the same -59.04, and this would be incorrect. Right? That would be incorrect. Because your calculator thinks that you are down like this. So how am I going to recover this angle? I can add 180, right? Because if I'm supposed to be down like this, come back up. Let's see. Let me draw it so you can see a little better on a unit circle. I'm going to kind of exaggerate it. It's telling me that my angle is this angle, right? That's what it's telling me. But my angle is actually that one right there. It's from the origin like this, right? Like that, instead of down by that much. So we can just add 180 degrees to it and we will have the correct angle. So what is that plus 180? 120.96 degrees. All right, do you remember last class I told you what happened if you multiplied a vector by negative? What it does to the vector? So like, let's say this vector is pointed this way and I multiply it by a negative number. What does it do? What does the negative do to it? Opposite direction, right? Can you see this vector right here? That if I multiplied it by -1, that essentially what that would do is like distribute through and make this -3 and +5. And so these two vectors, it's just like, you know, this way, pointed that way, we multiply it by -1, it's pointed the other way. Right? Okay. I just wanted to point that out. All right. Let's try something different. This one's going to be a little harder. I have a vector. I'm going to tell you that the length of V is 7. And I'm going to tell you that this angle right here is 33 degrees. Now notice my notation there. I put the length of V is 7, right? The length of V is 7. When you see that, what we're saying is if you measured from tail to tip, that would be 7 units, right? It is not correct. If I were to have written V is 7, I am not saying that does not mean that the length of V is 7. This is actually terrible notation, and it's completely wrong. Because a vector cannot just be a single number. It has to be angle brackets with your components, all right? So that's bad. This is the way I let you know the length of this is 7, okay? That's going to become important. That's going to become very important in just a moment. All right. What I'd like for us to do now is I'd like for us to determine the component form of this vector. So that's the instructions here. Find component form of the vector, of vector V. Thoughts on how we could do this?
Yeah.
What do you think?
Circle is going to end up making a right angle, right?
Yeah, we could create a right triangle out of this again. This is why we do vectors after we've studied the trig, because everything is kind of triangular here. So if we come in here and we, say, all right, there's a triangle here, right? And we want to know what this side and this side are, right? V1 and V2. We basically what we're looking at is this. We've got right triangle. This side's 7. This is V1. This is V2, right? And this is 33 degrees. That's all we have right here. So can you give me what V1 is? Yeah, you can do different things. It's a right triangle, though. Because it's a right triangle, we don't need law of sines or cosines. We can just go with our straight-up basic trig functions. So is there a relationship that you can create between this angle, this side, and that side? What is the relationship we have? Cosine, right? So if I wrote down cosine of 33 degrees, that should be equal to what? V1 over 7, right? So 7 times cosine of 33 degrees is V1. Multiplying both sides by 7. So we get on our calculator, and we're going to get a decimal because I gave you a weird angle. Make sure you're in degree mode. 7 times cosine of 33 degrees. 5.87. 5.87 is V1. And that is the horizontal displacement, right? Now, to get V2, I need to use a different trig function. What trig function will I use to get V2? Sine, opposite over hypotenuse. So I can write down sine of 33 degrees is V2 over 7. So 7 times sine of 33 degrees is V2. And then you go on your calculator, and you get 3.81? Yes? Okay, 3.81 is V2. And that's what we were asked for, the component form of a vector, of the vector. So I can say the vector v, angle bracket, 5.87, comma, 3.81. Close it up. That's it. We've answered it. Is that pretty straightforward? So in the previous example, I drew a vector. I asked you to come up with its component form. I asked you to find its length, right, and its direction. Here, I gave you a picture. I gave you its length and its direction, and you came up with its component form. I could now ask you for its length, couldn't I? But you have it, right? So there's no sense in that. Direction, we were given, right? So it's kind of, what I'm getting at is this. If someone gives you the length and the direction, you can come up with a component. If someone gives you the component, you can come up with the length and the direction. So it's going to go like one way or the other. Let me try and summarize all of this with one final, like, general picture that shows all the relationships we have with a vector. So kind of a final summary here. You've got some vector here, v. The distance from here to here, I would represent with what notation? The absolute value thing, right? So this right here is the magnitude of v, right? This is an angle. Right here, we'll call it theta. That's the direction. If we were to extend this down into a right triangle, like this, the distance from here to here would be what? V1. And the distance from here to here would be V2. And now let me write down all the different formulas we have that go with this picture. We have that, well, V is the angle bracket V1, V2. We have that the magnitude of V is the square root of V1 squared plus V2 squared. We have that theta is arctangent of V2 over V1. We have that V1 is something and V2 is something, but I have not established that. I'm going to establish two new formulas that I haven't given us from this picture. We just did this a second ago. We found the components, didn't we? And we used trig functions to do it. So if I wanted to figure out what V1 was here, I could use the angle V1 and the length. And what would that equation look like again? I'm going to do it on the side here. If I'm trying to find V1, it would be cosine of theta is V1 over magnitude of the vector, isn't it? V1 over the magnitude of the vector. And if I solve this for V1, I have magnitude of vector times cosine theta. So that's the formula for V1, magnitude of the vector, cosine theta. Understand that? Without doing it, what would V2 be? Without actually writing it down, do you think what would this need to be? Magnitude of V, and instead of cosine, sine theta. That's it. This is it. This is the summary of everything here. This is for vectors in two-dimensional space. There are vectors in three-dimensional space, but we stay away from that here. There's inherently a problem in three-dimensional space with direction. Just think about, like, on a flat sheet of paper, we can all agree, like, going out the x-axis that way is 0, and then we can say, you know, positive angles. But when you're in three-dimensional space, like, what are we going to represent as 0? Like, which way are we going to point that's 0 for everyone? And then imagine that we all agree that that's 0, right? then what's 20 degrees? Is that me going 20 degrees like this, or 20 degrees like that, or 20 degrees like that, 20 degrees like that? So imagine like a cone all around this direction that's 20 degrees. It becomes a little problematic. We have ways around it, but we use, what we wind up doing is we come up with new coordinate systems. We have, in three-dimensional space, we have three coordinate systems that we use. It's Cartesian, cylindrical, and spherical coordinate systems. But again, that's beyond the scope of this class. It's something you'll get into if you go into Cal 3. Now, there's also another coordinate system in two-dimensional space. This is called Cartesian, like x, y. It's called Cartesian. There's another system called polar coordinates. We will talk about that next time, next week. Start polar coordinates. All right, how does this feel to you? This seem okay? All right, let's do a word problem. So I think you're ready. I think you're ready. It's not even really a word problem. It's more like an application, all right? Remember, vectors, I tried to motivate the idea of a vector with the idea of force, and I was messing with the mouse and the cable and doing all this stuff, right? Okay, so let's take a look at this situation where we have, let's say, this ceiling, okay? So like a support, like the ceiling, the roof right here. And then tethered to this ceiling from two anchor points, we are going to suspend a weight from this, from those two anchor points. But we do it in such a way that we're going to use two ropes to suspend this. These ropes are not equal length. Okay, so I have a rope over here that, let's say, is only about that long. Then I have a longer rope over here that's about this long. And then we are suspending this weight from the two ropes. Understand the picture? Yes? Can you imagine that real world situation, like rope? Yeah, there might be, they're never going to be completely straight because there'll be a little bit of a sag for its own weight, but let's just theoretically imagine that this is straight line, and weight. Yes? Why doesn't it like move over to the side and like find the middle? I should have brought some. This is actually, this rope is like tied to an anchor point, so this is not sliding along this rope, all right? It's anchored here, so that's stretched tight. This one is stretched tight, and it has found what we call its equilibrium point. It is static, it's not moving, all right? There it is. Now the weight, I'm going to tell you how much this weighs. Let's just go with 100 pounds, keep things simple. LBS for pounds. It's a 100-pound weight. I'm also going to give you the angles that those ropes make with the ceiling. So this one right here, I'm going to say is 38 degrees. And I'm going to say that this angle right here is 18 degrees. Does anybody have any idea what I'm about to ask you? The length of the rope? Okay, maybe.
The distance from the ceiling to the...
The distance from the ceiling to the weight? When you see 100 pounds, 100 pounds is a measurement of what? Do we all know what pounds measures? Okay, mass. Any other? Density? Okay, it's all right. We should understand what this is before we proceed, all right? Your weight, how much you weigh, is a measurement of force. It is not mass, it's not density, it's force. So look at it this way. We live on Earth, okay? Here we are. Here I am, standing on Earth, enjoying my day. There is a very, I guess, universal property of matter that if you get a lot of matter together in one place, like the Earth is a big clump of matter, that it has a force inherent in it that wants to attract other matter to it, which is gravity. The more mass you have, the more matter you have in there, the more gravitational pull you have. In fact, I myself, you have a gravitational force. Okay, so like when we walk by each other in the hallway, you ever feel yourself get pulled into someone? No, because you can't measure it. It's so small, right? The gravitational force is so small you can't feel it. But it's there. It's just negligible. All right? The Earth is so big and so massive, and there's so much matter in it, that it's pulling on everything around it, including us, which is what's sticking us to the ground. Right? Okay, now, 2 weeks ago, I took a trip out to the moon. Was it 2? I think it's been 3. 3 weeks, I went to the moon. And when I got there, the moon was a lot smaller, which meant there was a lot less matter. And that meant that the moon had a gravitational force to it, but it wasn't as strong as the Earth because it's less matter. My matter had not changed, right? The amount of matter in my body had not changed. What changed was the amount of matter on what I was standing on, right? What I was next to. So the force got smaller. So on Earth, I think it's a third. You weigh about a third of what you weigh here. 6, whatever. Not important. The fact that I got there was important. And back, okay? So your mass, okay, how much matter you have is mass. And that doesn't matter where you are. Okay, if you're on Earth, if you're on the moon, your mass is the same. What matters, your weight, is computed by somehow computing something with your mass and the force of gravity. In fact, you've probably seen this. This is Isaac Newton's force equals mass times acceleration. Acceleration, that's A, is the force of gravity. So on Earth, the force of gravity is 9.8 meters per second. That's the measurement. You multiply that times your mass, and that will give you your weight. So this right here, measurement, is a measurement of the force, mass times acceleration. Are y'all okay with that? So yes, the question here is exactly that. That's very good.
Because as a joke, I was going to say that.
Really? Yeah. What planet are we on?
I was going to say that, and I wish I would have.
So if you weigh 100 pounds on Earth, you're not going to weigh 100. Well, if you weigh 100 pounds, you need to probably eat. But that's probably inappropriate. I'm probably going to lose my job for that. I've offended somebody. Okay, whatever. Did I tell you I was giving my dog the dog bones the other day? Just wanted to nibble off of it. I can't believe I told you I want to be a German Shepherd. That was. I told my wife about that. She's like, "You're crazy." All right. Force. The big thing here is I'm trying to make sure everyone understands that weight and mass are not the same thing. Okay? Weight and mass are not the same thing. So when we look at 100 pounds, we're looking at the weight, which is a force. The key is that it's a force. The question here is, what is the tension in the two ropes? That's what I want to know. So tension in a rope is a force. So I want to know how much force is on this rope and how much force is on this rope. Because we know certain ropes, you pull them hard enough, they'll break, right? So we want to make sure that these two ropes can support this weight. Is it possible that the force on those ropes is greater than 100 pounds? You think so? Even though the weight here is 100, you think I can actually get more than 100 pounds in these ropes? Do you think that the sum of those two has to be 100 or no? Okay, so that's what we're about to find out. what we're going to see is that the force in these ropes is